This is lesson 3 in the Redox and Electrochemistry unit. So at this point you know how to find the oxidation states of elements, you know the definitions of oxidation and reduction, and how to identify if a reaction is a redox reaction. You also understand the definitions of an oxidizing agent and a reducing agent. Today you're going to look at how to write the half reactions for a redox reaction, which basically is just writing out the oxidation portion and the reduction portion, including their electrons, and then how to balance those reactions in a very simple way. So this do now question in the following equation, what is the oxidizing agent? So first of all, when you ever see oxidizing agent, you should right away recognize that the process under the oxidizing agent undergoes is actually reduction. So you want to identify the substance that is being reduced. So we're going to go through and look at the oxidation states really quickly. Let me move this out of the way. We're going to do the oxidation states here. Copper is alone in the reactant, so that's 0. Silver on the reference table is a +1. Nitrogen has too many choices. Oxygen is a -2. So that means that the nitrogen would have to be a +5 to cancel all that out. On the product side, the silver is alone, so that's a 0. Oxygen's a -2. Now the copper here, because it's paired up with nitrate, the NO3 polyatomic ion has a -1 oxidation state, and since there's one of them here, the copper has to be the +1 version of copper, and the nitrogen would be a +5. So now let's look at the changes that are occurring here. Copper changed from a 0 to a +1, silver changed from a +1 to a 0. So the substance that underwent reduction would be the silver. And we would pick the original version of the silver. If we were given a multiple choice question, it would be the silver +1 that underwent reduction and is the oxidizing agent. Okay, so now we're going to look at how to do these half reactions. It's very simple. The half reaction is going to show either the oxidation part or the reduction part of a redox reaction. So a reduction half reaction shows an atom or ion gaining one or more electrons, and the oxidation half reaction shows an atom or ion losing one or more electrons, and that all goes back to the Leo says Ger concept. Looking at these rules, it's kind of clunky looking at the rules here without actually seeing an example, so I'll just read through these. So you want to do the oxidation states in order to figure out who's being oxidized and who's being reduced, and then you just write down the symbol and the oxidation state originally, and then an arrow, and the symbol and the oxidation state on the product side for both the substance being oxidized and reduced. The last part that you have to do, that's the most important part here, is show how many electrons were involved in the loss for the oxidation part or in the gain for the reduction part, and they have to be on the appropriate side of the arrow. So here's an example. We have this redox reaction. You could also classify this as what type of reaction. If you were asked to classify as synthesis, decomposition, single, or double replacement, what kind is this? This is a single replacement reaction. So what we have to do first is track the oxidation states. So originally the copper is a 0, and at the end the silver is a 0 because they're free elements. The silver in the reactant side is a +1 according to the periodic table. Here's a quick little hint for you. If you have a polyatomic ion that stays identical on both sides of the arrow, you know that it didn't change, because if it's NO3 to begin with and it's NO3 to end with, neither of the oxidation states of nitrogen and oxygen changed. So that's your spectator right there. It didn't actually participate in the redox process. So we know their numbers aren't the ones that are changing here. It's the silver and the copper that are. Those are the ones that are swapping. So the copper's oxidation state in this compound is a +1 in order to cancel out the overall -1 charge on the nitrate ion. So now we can write down our numbers here. So copper went from a 0 to a +1. So what process is that? That is oxidation. And then we just write down the changes that occurred. So silver underwent reduction from a +1 to a 0. So this is how you're going to write the half reactions. I'm going to write them over to the side here. So I'm going to write down copper 0, arrow, copper +1. Okay? Now, because copper was being oxidized and it lost an electron, think of it like as releasing an electron. When we were doing the kinetics concepts and we were talking about endothermic and exothermic reactions, an exothermic reaction releases energy. If it's being released, what side did we write the word energy on for an exothermic reaction? We wrote it on the right-hand side. So likewise, when we're talking about electrons being lost or electrons being released, we would also write those electrons on the right-hand side. So how many electrons did that copper lose in order to change from a 0 to a +1? It lost 1 electron. So I will add 1 electron to the right-hand side. Now, we never want to do subtraction in an equation. We always want to do addition here. So this makes sense. Look at the charges here. 0, that arrow is my equal sign. +1 plus -1. Is that a correct arithmetic equation? Yes, 0 equals +1 plus -1 because electrons are negative. So it makes sense to put it on the right-hand side. And then for the silver started out as a +1 and it changed to a 0. Well, how does it go from a +1 to a 0? It gains, because it's reduction, it gains 1 electron. So if it's absorbing or gaining an electron, we would add that electron to the left-hand side. And again, mathematically, this makes sense. +1 plus -1 equals 0. Okay, so that's the most important part, is understanding that in an oxidation half reaction, the electrons that are being lost get added to the product side. In reduction half reactions, the electrons being gained are added to the reactant side. So here's a couple examples we can work through here. So in this first one, we can see that the mercury starts out as a +2 and it ends as a free element, so that means a 0. And here we have iodine starting as a -1 and iodine's ending as a 0. We can look at this taking the 2's into consideration for the iodines, and we could also look at it without. So let's look at the mercury first. So what process did mercury undergo here? Mercury underwent reduction. So we're going to write down Hg +2, arrow, Hg 0. Now how did it do that? How many electrons did it gain? 2. Since it's reduction, what side of the equation do we put the electrons on? We put them on the left-hand side. So 2 electrons were gained. So that means that iodine underwent oxidation. Going from a -1 to a 0 is moving in the positive direction, so that does mean that it was oxidized. So I'm going to write down 2 iodine -1s, just like I see it in the equation, arrow, and then I2. And the reason we write it like that is because it's one of the Brinkelhoffs. When it's a free element, it has to be in sets of 2. Now, if 1 iodine went from a -1 to a 0, that's a loss of 1 electron. Since this equation has 2 iodines moving from a -1 to a 0, that means it has a loss of 2 electrons. Okay, when you have a balanced equation, the number of electrons gained has to be equal to the number of electrons lost. If you wanted to write it this way, showing what happens to one of them, that's okay. It just wouldn't, you wouldn't be able to plug it back into the original equation that way because the numbers wouldn't be balanced. But if you just wanted to show what happens to one, that's all right. Okay, so the second equation here, what type of chemical reaction is that? We can classify it as redox because we have a free element on one side and it's no longer free on the other side in the cases of both the magnesium and the chlorine. But how else could we classify this reaction? This reaction could be classified as synthesis. So you could get credit on constructive response with either of those. So let's track our oxidation states. Magnesium on the reactant side has an oxidation state of 0. Chlorine on the reactant side, free element, 0. Product side, magnesium is found in which group on the periodic table? It's found in group 2, so it must be a +2. So that means that each of the chlorines has to be equal to a -1. So track the changes. Magnesium changed from a 0 to a +2. What process is that? That's oxidation. So we can write down magnesium 0, arrow, magnesium +2. So that's 2 electrons lost. We add them to the right-hand side. The +2 plus the -2 equals the 0. And then for reduction, it would be the chlorine. So we have 2 chlorines changing into 2 chloride ions. That's how you would reflect that on the product side, 2 chloride ions. We don't want to do this because that makes it appear like it's a polyatomic ion. So we always want to flip that subscript over and make it a coefficient. Now, how many electrons did it take for 2 chlorines with 0 oxidation state to change to 2 chloride ions with -1 oxidation states? It would take 2 electrons. If you're given an equation and you have to balance the charges, you just have to keep track of how many electrons are lost and how many electrons are gained and make that equal out by doing coefficients. Again, these rules are kind of clunky, so I'll show you an example. So here we're given just the net, this is called the net ionic equation. All we're doing here is showing the important stuff. We omitted the spectator ions and are just showing what is going on with the elements that are changing in their oxidation states. Now, if you were just to look at this and it said balance this equation, you're like, well, wait, there's 1 magnesium on each side, there's 1 chromium on each side, it's balanced already. But it's actually not, because if you look at what's going on with the charges here, the charges are not balanced. The original oxidation state of the magnesium is a 0. The final oxidation state of the chromium is a 0. So the way that this is written, and this is how you can solve these, the magnesium is losing 2 electrons to change from a 0 to a +2, but the chromium is gaining 3 electrons to go from a +3 to a 0. When you have a balanced equation, you have to have conservation of mass, energy, and charge. And that's the one that we haven't looked at this year until now. So what that means is in a redox reaction, the number of electrons lost has to be equal to the number of electrons gained. Now, when you have something involving a 2 and a 3 and you have to equalize them, I have to find their least common multiple. And the least common multiple between the 2 and the 3 is a 6. Well, how do I turn this 2 into a 6? I multiply the substances that it's touching by 3. So now 3 magnesiums changing to +2s would involve the total loss of 6 electrons. Now, how do I change this 3 into a 6? I throw a 2 in front of the chromiums, because now 2 chromium +3s changing to 2 chromiums with 0 charge would involve the gain of 6 electrons, which means that it's balanced. So this was a Regents multiple choice question. When the equation is properly balanced, using the smallest whole numbers, what's the sum of the coefficients? The answer would be 10, because we're just going to add all those together. Now this next one that says balance the redox reaction, if you're given the full equation and you're asked to balance it, I don't care how you balance it, just get it right. So like this first example, there's really no other way for you to balance this except by looking at the electrons, because they don't give you the full equation. But when they give you the full equation, like in the second example, just make it work. So if we just eyeball this one, we have 1 nitrate here and 2 nitrates here, so we'll put a 2 there. Well, that gives us 2 silvers. We put a 2 here, and we're done. Okay, so nobody cares how you balance it if it's a full equation. But if it's only the net ionic equation, you have to use the electron method. Here's just a couple of Regents questions to wrap this up. So here's one: given the balanced equation representing a reaction, when the iron atoms lose 6 moles of electrons, how many moles of electrons are gained by the copper ions? You don't even need to go through any sort of math here. It tells you that it's balanced, and all balanced equations have conservation of mass, energy, and charge. So if the irons are losing a total of 6, how many do the coppers have to gain? A total of 6. That's it. It's already balanced. Here's another one. Given the balanced equation representing a reaction, what's the total number of moles of electrons lost by magnesium when 2 moles of electrons are gained by the nickel? Oh, okay, it's balanced, so 2. It does make sense, because we have no coefficients in front of these, so that means that 1 magnesium is losing 2, and we have 1 nickel gaining 2, so it does work out. This top one, which half reaction correctly represents reduction? So the first thing we want to think about is what's going on with reduction. With reduction, you have a gain. When you're gaining electrons, they have to be on the left-hand side. So that means that 1 and 2 have to be out because the electrons are in the wrong place. The other thing we have to look at with reduction is that when something gets reduced, its oxidation state gets reduced. It goes from a higher number to a lower number. So which of these involves the oxidation states correctly going from a higher number to a lower number? It has to be choice 3, because we end up with a positive 4 plus 1 electron, which is negative, bringing us to a positive 3. Whereas choice 4 says a positive 4 plus a negative 3 is a positive 7, and that just doesn't work. 42 is just recognizing a redox reaction. So again, the easiest way for you to recognize a redox reaction is find a free element on one side and that same element is not free on the other side. So which one is it? It has to be choice 1. Oxygen's a free element here. It's not a free element on the product side. How else could you classify this reaction? This is a combustion reaction. Choice 3 and choice 4 are both the same type of chemical reaction. What type is that? That's a double replacement. And then choice 2 could be classified as double replacement, but you could also classify it another way that's more specific. How else could you classify this one? This would be a neutralization reaction because we have an acid and a base making a salt plus water. We'll look at the second one here, given the unbalanced ionic equation. So this is one of those skeleton reactions. When this equation is balanced, both the iron positive 3 and the iron would have what coefficient? So in order to fill in the incomplete coefficients, let's look at the complete ones, the magnesium. So we have 3 magnesiums changing from 0 to positive 2. So how many total electrons were being lost by those 3 magnesiums? It would be 6 total electrons, okay? So 6 electrons lost. So that means that it has to be choice 1 or choice 2 because we need to have 6 electrons being transferred. Now, what is going on with the iron? The iron starts out as a positive 3 and ends as a 0, which means that that one iron gained 3 electrons. Well, we don't want one iron to gain 3 electrons. We need to match it up with 6 electrons being lost. So what coefficient would I have to put in front of these irons to reflect a total gain of 6? I would have to put a coefficient of 2. Okay, so that gave you an overview of how to balance these equations using the electrons and also how to look at half reactions. So now your job is to complete pages 11 through 14 in the redox packet. This is your responsibility. You have to get through this so we can move on to finish up this final unit.